Hi, everyone. Thank you for that introduction. I'd also like to introduce myself as your friendly neighbor. I'm a third year at UW School of Oceanography, and thank you to Ethan for that lovely presentation. I'm now more concerned about my ride home than I am about giving this presentation. Okay, so I've been a proud ocean lover since 2004. Here you can see me in 2004 celebrating my 11th birthday by enjoying a cake representing the popular marine biology that was extremely popular in the early 2000s. And then here in 2024, which when making this presentation I thought was only 10 years later, so I was very quickly humbled, I am at the Ocean Sciences meeting that was hosted in New Orleans just this year. And so you might be excited to talk about some pretty cute ocean animals. I wish I was talking to you all about these today, but I'm going to be talking about some smaller things that do impact these animals. But these are a couple of my favorites that are impacted by what we're going to talk about today, which is ocean acidification. We've got our sea lion, our sea otters, and our beautiful great white shark. You may not be as convinced as I am about his cuteness, but what if I showed you this? All right, so you might be wondering, how does someone get into ocean chemistry? How does that even come up? So I actually grew up in a small cow town in the middle of California, so I wasn't really aware of ocean sciences. I went to a small community college called Modesto Junior College, where I took my first chemistry course and failed miserably. I decided to take it again with the encouragement of the professor and got an incredible C+. And like any reasonable person, I decided that I would make that my career. But how am I going to communicate ocean chemistry to the general population? It's not a very straightforward concept. So I like to think of myself as a bit of an ocean plumber. Most of my family comes from the union, and so I have some plumbers and some welders in my family, some nurses, and I like trying to communicate science in that hands-on way. So if you could trust me for a moment to close your eyes, I will walk you through how the ocean might relate to plumbing a little bit. So if you close your eyes, you're going to imagine you're renting an apartment in Seattle where it rains a lot. Unfortunately, your landlord is not very supportive and has not fixed the leak in your roof. And one morning you wake up and you step out of bed and you notice that there's way more water in your apartment than you're used to. You know that there's some damage to the floorboards, but you're not used to your feet being completely soaked. You jump up, kind of panicked, and you go to check the kitchen, and you check the bathroom, and you realize you think you have a leak in the bathroom. Okay, go ahead and open your eyes. Who are you going to call? Now, if you thought Ghostbusters, you probably knew exactly what I was talking about when I said the 2000s trend of marine animals earlier. But I would recommend calling a plumber, specifically my Uncle Joe, seen here on the left. And he's there with my mom. I decided not to cut her out of the picture because Mother's Day was yesterday, so happy Mother's Day to anyone in the room who resonates with that day. Uncle Joe is going to come into your house, and he's going to walk around assessing the leak in your home. And he's going to assess your kitchen and assess your bathroom, and he's going to say, yeah, most of this is coming from the leak in your roof. You really need to get that fixed. However, about maybe a quarter of this excess water is coming from this leak that you have in the bathroom. Now, how the heck does a plumbing issue relate to the ocean? What if I told you that we actually do have somewhat of a leak in our ocean? Now, I'm not going to argue with you about whether water is wet. I don't have time, but I do have opinions, so that is a question suggestion. But it's a bit of a different leak. So most of you are probably fairly familiar with carbon emissions. You hear about it all the time in the news, and there's all types of climate anxiety stemmed from it. So we've got CO2 coming from all of our transportation and smokestacks and all of those types of things. But what happens is you could imagine these 4 clouds of CO2 being all of the CO2 that gets accumulated in 1 year. And what actually happens is the ocean absorbs roughly a quarter of that annually. And so you might think, well, it's only 25%. Who cares about 25%? That's just a little bit, right? Let's walk through just how much 25% actually is. So we're about to look at a graph of annual CO2 emissions, starting from the Industrial Revolution up until our most recent marker, the pandemic. And so on the x-axis on the bottom here, we have our timeline. And then, unfortunately, these are the numbers of our y-axis, going up to 35 billion tons. This is what the numbers looked like pre-industrial revolution, and this is what those numbers look like post-industrial revolution. So 25% of that is a ton. It's actually a couple billion tons. So what's the damage in a chemical flood? Obviously, our floorboards aren't getting soaked, right? But something else is occurring when this excess CO2 is entering our oceans. And what happens is when that excess CO2 enters our oceans, it drops the pH. There's chemical changes that occur in the ocean that decrease the pH of the ocean, generally speaking. And an example of pH is if you've ever seen anyone who needed to adjust the chemicals in a pool or a hot tub, they're adjusting the pH usually. And you can also think of this as if you were to bite into a lemon, it's very acidic and you're gonna pucker up because of that acid. Whereas if you're cleaning with bleach, it's a more basic solution, which is why it's cleaner. It can damage viruses. We call this process of that pH decrease ocean acidification. And even though Ethan spared you the chemistry, I'm not going to be as kind today, but I did fail that chemistry class, came back and got a degree in it from the University of California, Davis. So if I can do that, I trust that you can get through this presentation with me. We will go step by step. And so what we're going to start with is up at the top, you see these red arrows coming down. And those are our CO2 molecules entering our ocean. And I promise this is probably going to be the only chemical equation you'll see today. But so we've got our carbon dioxide, and we've got our water that's in the ocean, and then you can see this little shell. And that's one of our most fragile creatures where this is relevant, and it's involved in a lot of food systems. You can think of this shell as like a mussel or an oyster. So when we, in addition to that, there's also these things in seawater called carbonate ions, and those are the base product of what mussels and oysters and other animals that have shells use to build their shells. But don't worry about the chemical name. You could just think of it as this mineral. I call it aragonite. There's also calcite, but we'll just say minerals for now. And what happens when we add a bunch of CO2 on this first side of this equation is we increase the product of bicarbonate ions, but don't worry, we can just call that acid. And that is increasing the acid drops the pH. And so what this does is it ends up creating stress on our organisms. So you can see some nice, happy oysters from Taylor Farms and our Great Barrier Reef, probably a older picture or a less impacted area of the reef. And then this is what some things look like today, with also the Great Barrier Reef on the right. And then on the left here, we have a picture from a paper showing, I believe these are, I can't remember if they're oysters or not, but a shelled organism in its larval stage, a baby stage, where it's trying to develop that shell. And some of it is being developed in a lower, a situation where they have less of that mineral, and another one being developed where they have enough of the mineral. So you can kind of see that shell on the right struggling to properly develop. So if you're anything like me, this should cause a little bit of anxiety about how to take care of our oceans, and we start to think about how can we stop it. And obviously, one of the best ways to make changes is politically, getting political support on protecting our oceans, making changes that impact these CO2 emissions. But as we all know, that can take a lot of time to make those changes. So going back to being an ocean plumber, like my uncle, I like to start to think about what are the solutions that I can come up with as a scientist. And so when I'm thinking about this, we have to start thinking about this is like a very widespread issue. Are there smaller ways that we can tackle this? One way to think about this is that if I was an actual plumber like Uncle Joe, different neighborhoods might experience different plumbing issues, right? Some pipes may be super old, not able to flush toilet paper, and other pipes, like the one seen on the right in Flint, Michigan, have maybe made with different properties, or the water running through it may be being chemically treated differently. So I have to start thinking what's happening in specific regions of the ocean, and could those happenings differ based on location? So in my research, these are all of the areas that I'm looking at. All of the yellow circles are locations where I'm using buoys, and all of the red diamonds are locations where there are regular ships that go out to collect data. And what that means is these are two examples of how that works. On the left, we have an example of one of those buoys. This is an instrument that sits on top of the water, and it collects data from the water by having sensors that are just barely submerged right under that buoy. And then this one in particular is set up to also collect atmospheric information, so you can get information about what's going on above the water as well. The shipboard water sampling happens in a few different ways. The one I'm showing you today, that's called a Rosette CTD. I think it's super cool. It's made of multiple cylinders that are all open before it goes overboard, and they send it to the bottom of the ocean, or not the bottom of the ocean, but as far as they want to send it down for testing. And as it gets dragged up, they close them at they close each cylinder at a different depth, so you can get different chemical properties down that water column. For my research in particular, I'm mostly focused on the surface, but it can be helpful information in other settings. So what might be happening differently at these different locations, right? Like, I'm not working with different pipes, but the water and the environment might be very different. I'm looking for differences in things like how salty the water might be. Is the temperature a difference? Are there differences in the freshwater inputs? So is there fresh water coming in from rivers? Is this an area where it rains a lot? What are the chemical differences happening in the water? And are we looking at a coastal environment versus open ocean environment? These all can make have very different impacts on what's happening in the ocean. So I'm going to share with you some really early results of my work. These are from 2 locations, one which is considered open ocean, just off of Hawaii, and another that's pretty coastal and pretty local to us, just off the coast of Tacoma. And so what I'm looking for is changes in that mineral I was talking about before, where those, oysters and clams need to build their shells. And so what I've seen differently about these locations is the open ocean location in Hawaii has a pretty significant decrease of that mineral over time, whereas kind of unexpected, the Tacoma location has an increase over time, which is better for those organisms and better for anyone who likes to eat or needs to depend on those organisms. And then when I want to know what is happening differently at these locations, I start to look at those things we just talked about, what's happening with the seawater chemistry, the fresh water, and the temperature. And these numbers aren't super important for this talk, but what is important is that we notice they're pretty different. You see a pretty high impact from seawater chemistry at the open ocean location, whereas the coastal location has a pretty big distribution in things that are causing the changes. Now, the reason that it's important to understand why there's different things happening in different places is because getting a grasp on that allows us to make region-specific changes to improve those locations. So one thing that I think is pretty cool that's already being implemented in some places is kelp and seagrass cultivation. So a pro about this is, say that you're trying to promote an oyster farm, right? If you start, what early science has shown is that putting kelp or seagrass cultivation near that oyster farm can actually offset the impacts of ocean acidification, because what's happening is that seagrass or kelp is breathing in some of that excess CO2. Kind of the same way we think about trees. We're always saying plant more trees, right? If you saw James's talk, you might not always say that. But in terms of this, it's actually pretty interesting. But again, thinking about region-specific changes, putting an extra kelp or seagrass cultivation experiment in the open ocean might not be super helpful, right, if we're talking about oyster farming. Also, it might not be the most quick or feasible option. So another option is, anyone ever had one of these Tums? Not sponsored. It says, if you read the back of the label, Tums is basically calcium carbonate, and carbonate was the base product of the minerals that we were talking about earlier. And so when you're feeling all that extra acid in your stomach and it's kind of, you got that heartburn, you take that antacid. And so we're starting to think about, how do we do this in the ocean? And to some degree, the ocean already does this through a process that we call weathering. And what happens is, when it rains on the coast, over time, rocks are broken down, and you'll get an influx of carbonate into the ocean. And so something that's being worked on, not exactly to that description, but is, can we add minerals to the ocean that would kind of act as a bit of an antacid? So all of this is pretty new, at least my portions to it. And so just like how I got through that chemistry class and decided to push on with my career, we as a scientific community, including you all, need to just keep swimming and keep engaging with science. Thank you.